presentation. So our first speaker, it's Elizabeth Hero. She's from BP, and she will elaborate on what BP is doing about these topics. Then we'll have Weichang from Saudi Aramco, then Detlef from Shell, and I will close the short presentations. And then, because this is above, we will have an open mic discussion, questions and answers. Elizabeth?
Thank you. I'm going to have to figure out how to... I'm going to hold the mic in the right hand, and then we'll see. All right, is this okay? You can hear me? Yeah, so good morning. My name is Elizabeth Lheureux. I'm the head of HPC at BP here in Houston. And what I've got are just a couple slides on what BP's strategy has been in the energy transition and our ambition to become net zero. And so I'll talk through that a little bit. And then how that impacts what we do in HPC and what we do in technology in BP and where we're heading in the future. So if you have any questions, feel free to interrupt. We can make this a little less formal, I think. So as you might have seen in the news, right, a couple of years ago, actually just before the pandemic, BP announced its new ambition, which was to become net zero by the year 2050 or sooner. And that is underpinned by our desire to transform ourselves from an international oil company into what we're calling an integrated energy company. So that means shifting our focus a little bit from producing resources or simply producing resources to delivering integrated energy solutions to our customers. So we're focusing on a variety of different customers, so everything from the individual consumer to power and energy companies to cities who want to decarbonize, and so we're partnering with various cities around the world as we do this. This also means that we're focusing a little more on different types of energy, so renewables are becoming a big part of our portfolio, non-hydrocarbons, so hydrogen and biofuels and things like that. So the strategy to get to this net zero ambition is really divided into three different components. And these are three equal pillars, I'd say. So there's the resilient and focused hydrocarbons. And what that means is really focusing on the highest margin and lowest emission barrels that we can produce. And so our strategy is underpinned by several different aims. And one of the aims, for example, under hydrocarbons is to reduce production by volume by 40% by the year 2030. And that's been a big number that a lot of people have spoken about in the media. But what it really means is we're focusing on, like I said, the highest margin barrels. So focusing on the most cost-performant resources that we can produce to sustain earnings while reducing that volume of production. The next focus area in our strategy is convenience and mobility. So that's really focusing on the customers and their retail and mobility experiences. So customer touch points, and for example, an aim in there is to increase the number of electric vehicle charging points to, I think it's 70,000 by the year 2030. And that's up from 7,500, I suppose, when the strategy was announced 2 years ago. And then the final focus area of our strategy is low carbon electricity and energy. So shifting our focus to new energy sources like renewables and bio and hydrogen, like I just said. And so hopefully the earnings sustained in our hydrocarbon businesses will support this growth in new forms of energy. And so the intent also is to use our size and scale and technical experience to influence various parts or touch various parts of the value chains. So for example, coupling CCUS projects or carbon capture projects with power generation plants and using our skills to touch all of these different areas. Okay, so BP is always, we've always thought of ourselves as a technology company. We've always prided ourselves on our strategy of leading in certain technology areas and being fast followers in other technology areas. And so as we go through this transition, what we're doing is kind of sitting down and evaluating which of these technology areas we can be good at. So how do we transition some of our skills that we excelled at in the subsurface space? How can we transition those to some of the new energy areas, as well as where we want to develop our new skills to set ourselves apart in this new renewables energy space, right? So experimenting with things like wind and solar and figuring out where we can differentiate ourselves in this new world. So you can kind of think of our skill sets as 4 different quadrants, right? We've got subsurface, traditional, as applied to hydrocarbon production. And that's everything from monitoring to fluids, simulations and understanding reservoirs, imaging the overburden and reservoirs, creating subsurface simulations and understanding rock properties and all of that good stuff. So all of that can be applied to the second area, right, which is green energy and low carbon energy, especially as it comes to carbon capture and storage and geothermal and some of these other subsurface related activities. And then, as we look at the other 2 quadrants of our activities, we've got everything that's sort of non-subsurface, right, above surface. So we've got applied sciences, thank you. Applied sciences who do experiments in CFD simulation, so computational fluid dynamics, looking at refining processes and fluids and corrosion and erosion and all of that, more focused on refineries, right? So all of those skill sets, we're looking at how we can take those into new greener energy areas. So looking at things like how can we simulate wind turbines in a wind farm, and how can we simulate the interaction between wind turbines, or solar panels and weather simulations. So as we become more of a renewables energy company, how can we look at the technology associated with solar and wind, which has a lot to do with weather, right? And then as we get into further down the value chain towards transportation and energy, how can we model energy distributions, use things like artificial intelligence to understand where the energy is going to come from as the clouds move in, as the rain shifts, and how we distribute that energy to our customers. So where do we stand right now in our HPC, in BP? I've put up a chart here of our typical usage, and you can see that probably close to 90% of our usage right now is subsurface related, and about 80 to 85% of that is geophysics. So that is really just producing subsurface images and understanding reservoir rock properties and reservoir fluid flow. And then we've got another portion of what we do in the applied science space, which is really around CFD. But if you look at what's happening in geophysics, and if you look at the trends of our usage over the past few years, those trends really just reflect our desire for increasing image resolution. So that's increasing the density of the grids that you calculate on, which naturally translates to increasing needs for compute. So we're expecting that need to continue into the future. We will still need to see into the subsurface. We will still need to see the subsurface clearly and at high resolution. And we will also probably have less tolerance, even less tolerance than we used to around uncertainty and risk. So that'll involve doing a lot of simulations and scenario modeling to understand not just the one deterministic answer, but the probabilistic space of answers around subsurface images. And I think we're also at a bit of a tipping point as well in geophysics, where we started incorporating more physics into our calculations. So we're not just simulating the acoustic part of the wave field anymore. We're simulating more of the elastic wave field. So we've got anisotropic parameters, we've got shear waves and density and attenuation, and all of that just translates to more calculations per step in your simulations. It translates to greater memory requirements as you need to hold more volumes of memory and calculate over them. So all of that is ramping up in our world. So we've, sat down last year and tried to predict where we were going in the future in HPC. And like I just said, we expect our subsurface space and geophysics to continue along its trend of increasing resolution and increasing computing demands. But what we're going to see is a shift in portfolio a little bit. So we think that geophysics wedge in the last pie chart will probably shrink a little bit, but it will still represent a growing demand for computing. But what's going to happen is we'll see shifts to a little bit more of the renewables scientific space. So, like I said, weather modeling or CFD simulations for wind turbines and that sort of thing. We'll probably see a big impact from machine learning and data science, which is becoming a big part of our company. As I said, subsurface algorithms will continue to grow. We've been very good over the past few decades at outstripping our compute capacity with our algorithms. So being more ambitious than we have capacity to solve our problems, right? And then the other thing we're noticing is that as we have all of these new parts of BP coming in and trying to understand what they can use HPC for, what they can use simulation technology for, we've got a lot of new people coming in and looking for help. So there's a large draw on our HPC skill sets, our developers, our system administrators, our operations team, just to try and understand how they can run their applications, how they can get them installed, how they can run them efficiently, and also sort of understand what our past experience is in places like geophysics where we've been doing a lot of work already. So for us, that really just translates to we need more people and we need more computers. And I think we've got sort of tentative agreement to grow our on-premise data center, and that's what we will be doing over the next few years. But if demand continues to grow as we expect it to grow, we will hit a limit at some point, and so we are experimenting with off-premise, let's say, HPC solutions. So whether that is things like cloud, whether that's partnerships with other companies in industry, or other labs or things like that, that's something that we're considering and looking into over the next few years. I think that's it. Some of the biggest opportunities for growth that we're seeing. I just kind of threw this up because these are the things we've been talking a lot about. And so geophysics, obviously everything I've said, right? Higher resolution subsurface images as applied to traditional hydrocarbons as well as carbon capture and geothermal reservoirs, but also sort of high resolution near surface imaging for things like wind turbine footings and anything else really that touches the subsurface. Weather modeling could potentially be a big growth area if we truly want to differentiate ourselves from the industry in terms of renewables. This could be the place to do it if we really want to be a technology-focused company like that. We're seeing a lot of demand for digital twins and robotics simulations, artificial intelligence to understand robotics behaviors, and that could translate to a greater variety of systems that we need in our center, things like accelerators. And then finally, in the renewable space, it's things like wind simulations with CFD. It's understanding weather patterns for solar panels. How can we apply all of our experience in artificial intelligence in those areas as well? So lots of area for growth. And hopefully we can, over the next few years, sort of settle into our new strategy and figure out where we want to excel in these areas. Thank you.
Well, good morning, everyone. My name is Weichang. I'm with Aramco's Houston Research Center. First of all, thanks, Mauricio, for the invitation, and good to see you all here. I will talk about some of the machine learning research development activities at the Aramco's Houston Research Center. This is support Aramco's upstream research and in general, but also I'll give you several examples that's specifically to energy transition. All right. So, in case the Aramco's research facility is not as familiar to you guys in this audience, I'm going to put up 2 slides just to explain. It's a relatively new facility. So Houston Research Center is the largest global research center Aramco has outside the kingdom. And it's a very compact size, but it covers a wide variety of areas. It's a primary upstream focused research facility. So we have the artificial intelligence team, which is my team, and then along with other traditional disciplines, drilling, geophysics, geology, production, etc. And it's quite integrated. And that's traditional being a strong research workforce for Aramco, now is being heavily focused on sustainability, energy transition area as well. So about two miles down the road to the facility. So the main facilities, it's actually located in Energy Corridor, about Park 10. And then 2 miles west, there's a separate building which is devoted to developing novel sensing technologies for oil gas applications. So here's a few examples where we measure flow measurements, sensing, downhole, distributed fiber sensing, and other type of physical sensing devices and systems. So they give us very good opportunity to work across different disciplines to integrated research development. So in the next few slides, I'm going to show you a few examples. Some are specific to energy transition. Some are more focused on just machine learning applications. That's my group's activity. So, so the first example is apply machine learning to fiber optic distributed sensing, in this case for CO2 sequestration. I'm showing here is actually a CO2 storage site field data set where we collected fiber optic gas measurement with a much wider coverage area, as well as the same time we have geophone measurement at a slightly shorter depth range. Then we look at both DAS and geophone measurement, and then to do imaging, and trying to figure out and compare the performance in both cases. Now where machine learnings come in is we actually use deep neural network to map the DAS measurement data into particle velocities. And then we'll compare the DAS predicted measurement at the 2 different depth range compared to the geophone measurement at a narrow depth range. And you can see that on the upper right corner, the DAS results give you very much bigger imaging performance than the other short depth range results. So this work is being submitted to SCG and in the recent workshop. So the second example is also combine machine learning with DAS. This is, of course, with hydraulic fracture monitoring for completion. So here we actually measure DAS DTS data during the fracturing phase, where the hope was trying to predict the pressure flow rates from the SDTS data. This could be a surrogate problem as well too in the production phase. So we took both the DAS and DTS data during the pumping phase, and then we measure actually. The reason we use the pumping data is we have the ground truth that's measured on the surface compared to production phase where we don't really have any ground truth, but the phenomenon is fundamentally the same. Now, after training, actually, in this case, the results shown here, it performs very well for in-stage training testing, but we apply the same to the testing on data from different independent stages, and that works out very robustly. So these are two examples combining machine learning with novel sensing. One is with CO2 sequestration, one is with hydraulic fracturing monitoring. I'm going to switch gear to geophysical problems. So there's actually one recent work we've published applying deep learning for seismic coherent noise removal, which in this particular case is a very challenging standing problem, is how to suppress coherent seismic noises. And this actually we utilize quite a novel framework of applying surrogate physics constraint in a deep neural network. Specifically, the circuit model is trying to enforce the relationship between shallow refraction events and the surface waves. So we incorporate that constraint that into the middle part, where with the signal, the noisy signal consisting of both the refraction events and the ground roll, send into the network to separate out. But as we separate those components, we also require them to be satisfying certain surrogate physics constraint. And this is trained over a large number of field data set, and you can see the separation does a very good job in removing the ground roll data. So, and then we also apply to a non-seismic application where we're interested in monitoring, in this case, is a continuous monitoring of fluid movement use crosswell EM. And this is, I'm trying to put up the formulation where the traditional least square inversion versus deep learning inversion can be compared. And the focus has been not just simply borrow whatever, open source deep learning methodology that's been developed elsewhere, but we are more interested in the generalization capability of those methods in this particular applications, because oftentimes we see overfitting. So in this case, we actually apply the deep learning-based inversion scheme onto realizations of quite different distribution. And then as you can see, this learning curve trend, clearly there is overfitting happening as you pass through certain stages. So based on these results, we actually developed a combined data-driven and physics constraint method to avoid overfitting and improve accuracy. And for those who are interested, you can refer to some of the publications referenced here. So these complete two examples on the geophysics application. And the last two examples actually on geology and petrophysics application. And now you might be asking why this has anything to do with energy transition. So one of the actually application is, as we care about storage and capturing, people care about the porosity, permeability, and treatability. So we have to look at the material as we subject them to certain fluid. And we care about the change in the rock subject to the fluid treatment. And here's an example where we see morphological change due to the fluid treatment. And we need to understand what compositional variations associated with this morphological change. And here we apply the sample through different stage of fluid treatment. And we have the morphological characterization coming from SEM. At the same time, we have elemental distribution that captured before and after treatment. And then we compare the initial versus seawater treatment, and then another stage. And these give us a very good morphological characterization of the variation. At the same time, we have this elemental variation based on these cross-registration. We're able to capture at the places where we see majority of the morphology change that's causing the porosity change, what is the actual compositional material that's being removed or deposited. So that become very useful in quantify not only the geometry, but also the compositional information. So the last example I want to show you is when people do a lot of storage formation evaluation, a lot of core samples and petrophysical data, such as well logs, become very useful. And as similar to many oil companies, we accumulate over time tons of core samples. How to digitize them, extract information efficiently in the automated fashion become a daunting challenge. So in this case, we propose to do automated core image analysis based on digitized image to predict the reservoir properties such as porosity, permeability, and grid density in an efficient and reliable way. So we applied, we actually developed a customized deep learning network model that can take core image and a gamma ray as input and then predict the grain density, porosity, and permeability. And the goal is we can avoid, by training the model on the samples where both the core image and the core plug data as a current truth. When the model is finished training, we can apply this model to a large quantity core images without having to do core analysis. That seems to be very important to can streamline the whole process and speed up and finish processing a lot of backlog the core sample process tasks. So these are all examples I have, and with that, I'm open for questions. Thank you.
And thanks to the organizers for inviting me. I will take about 10 minutes to talk about Shell in the energy transition. This is an HPC conference, and I will barely talk about HPC at all. Instead, I will talk to you about Shell's position in the energy transition and how our portfolio is changing. And then we can simply work backwards and look at what is going to be important to us and how HPC can impact what is important to us. And I'll leave that to you to ask me some questions. I'm not going to tell you exactly what we're going to do in high-performance computing, but I'm going to talk to you at a relatively high level about what we're doing in the energy transition. So this is the mandatory disclaimer slide. Usually all I say is it is available to you, it is important. The summary is please don't make investment decisions based on what I'm telling you today. But today it's slightly different because there is a new line on the bottom here. And I'd like to blow that up. In this presentation, we may refer to Shell's net carbon footprint, which includes Shell's carbon emissions from the production of our energy products, scope 1, our suppliers' carbon emissions in supplying energy for that production, scope 2, and our customers' carbon emissions associated with their use of the energy products we sell, scope 3. That is by far the largest emission source that we account for. Our internal operations, scope 1 and scope 2, are about 80 million tons of CO2 per year. Our combined scope 1, 2, and 3 emissions are about 1.4 gigatons, billion tons per year. So you see where the challenge is in moving to net zero. It is reducing what our customers do with our products. There's a wealth of information on the web. I'm not going to go into any details. Shell.com is a good source. I'd like to point you to Shell.com Digitalization as far as use of computers, use of digitalization, use of AI, HPC goes. There's a lot of information there. The Shell investment case is also not just one item. Right? Typically, we're a for-profit company generating, as publicly traded company, shareholder value is hugely important. If we don't do that, we're going to be obsolete very quickly. But there's more angles to it. I already mentioned to you achieving net zero emissions. This is a shareholder, an investment case for Shell. We have committed to this by 2050 or earlier. I'm expecting this to move to earlier more and more, to be net zero emissions. There's also a third one, which is powering lives. The growth in wealth and health and good living of the past couple of decades has been causally linked to the availability of affordable energy. We should not forget that 1 or 2 billion people on Earth, depending on how you define energy poverty, live in energy poverty. It's Shell's declared goal to bring the number of people living in energy poverty down. We can't forget and be selfish, sit in our own air-conditioned vehicles and homes and say, now we have to reduce emissions. We can't forget about those people. And finally, respecting nature, being environmentally friendly, reducing waste, making a positive contribution to biodiversity. These are the 4 angles of the Shell investment case. And I can stand here and pontificate all day long to you how good Shell is, but let's look at what the external world is saying. This is a paper from just a couple months ago in Science by the Grantham Institute, by Simon Dietz and colleagues. They look at 40 oil and gas companies and how ambitious their climate goals are, because the assertion is if the strategies don't match the net zero ambition, then whatever they do makes no sense. So here they compare the strategies, and they've come to the conclusion that only one company plans to reduce its carbon greenhouse gas intensity below the 1.5 benchmark. It's Oxy Petroleum. Do we have somebody from Oxy in the audience here? Okay, that's too bad. Oxy relies heavily on direct air capture of CO2 for their strategy. One further company plans to bring its intensity under the 2-degree benchmark. That's Royal Dutch Shell, now Shell. It's not Royal Dutch anymore. No other company has set a target ambitious enough to beat the 2-degree benchmark. And here you can see the graphs that they've made. This is emissions intensity as for sold energy as grams of CO2 per energy unit. And so the lower the graph sits between now and 2050, the better. Oxy sits here, Shell sits here, and some of our colleagues, Mauricio and Total, is not far away. So I just want to say this is really the challenge. And of course, the authors of that paper also say, well, strategy is nice, but now we have to watch what the implementation of that strategy looks like. So one more slide on that. Between now and 2050 is a very long time. It is hugely important what we do between now and then, because CO2 is a cumulative effect. It stays in the atmosphere for very long times. So bringing the emissions down between now and then, the cumulative emissions, that is the most important goal. Of course, our operational efficiency is in here, reducing the 80 million tons. And then things like digital twins, optimization of our assets for computation come in very high importance. But that's only 80 million tons. Providing low carbon power to our customers. Shell is already the largest renewable power provider in the US. We plan on having 2.5 million electric charging points by 2030, 500,000 by 2025. That ramps it up very quickly. Carbon capture and sequestration has to play a hugely important role for the climate goals in all scenarios. CCS is important. We have committed to 25 megatons per year by 2035. You may know our Quest project in Canada, 1 million tons a year already, but we're also involved in 8 others. Gorgon in Australia is another one. A shift to natural gas. We're already producing more energy in the form of gas than in the form of oil. That buys us time between now and 2050. Low carbon fuels, Elizabeth already mentioned that. Biofuels, hydrogen. And then natural sinks, nature-based solutions. We're aiming for 120 million tons per year being sequestered as carbon in the soil. That's ultimately what it is. We already have a nature-based solutions business. And if you want to know a little more or a lot more about what we're doing in this space here and in the high-performance computing, an example is a presentation this afternoon by Janaki Vamaraju. It's using artificial intelligence as a proxy for reservoir simulation with a special application to CCS, but she will explain this afternoon. I highly recommend that you attend this talk. Now, this is the only and the last slide where HPC even shows up. Just a summary, we use digitalization, high-performance computing, artificial intelligence to drive our existing businesses, but also to create new ones. And the pace of digital adoption is accelerating. We've published, that we have already derived in 2020. The 2021 numbers have not been published. $2 billion extra earnings. This is extra earnings over baseline through digitalization that includes HPC AI. We maintain a portfolio of 100+ AI-powered applications in development and deployment, 2 trillion lines of sensor data in our data lakes, 10,000 pieces, increasing by about 300 every week, of equipment being monitored for predictive maintenance, and therefore also to prevent leaks, fix leaks, all those things that generate emissions and also cost us money in our assets. Virtual reality, augmented reality, maybe less the virtual rooms, but you know, the virtual reality borrowed from gaming devices plays more and more of an important role. We have 2.5 million registered users of our Shell loyalty programs across the world. We have 5,000 members of a network, internal company network of what I call data science and AI amateurs. And we have a group of about 350 also growing professionals. So the amateurs and the professionals with degrees, PhD in computer science, data science, AI, computational sciences. With that, I want to stop and open it up for questions or open it up for the general Q&A. Have any specific questions to my presentation?
Actually, I'm going after you. So.
Okay, all right, good. Mauricio is next. You want to use this thing here?
So my name is Mauricio Araya. I'm HPC and ML manager at R&D Total US. So I have initially have a bunch of slides, corporate sanctioned slides, you know, with all the bits and so on. So I took some of those because that's what I can present on behalf of the corporation, but I add some of my elements to it. Especially, I had to adapt it to what is this context, right? A little bit of HPC and so on, but there's angles that have been touched by my colleagues here, like some of us, or most of us, start from different, going to transition. We don't have transition experts. That's the honest assessment. We are all either computer scientists or applied math or electrical engineers and so on, and now we are thrown into this. So we are being asked to do things that we were not really trained for before, and we have to adapt. So that's part of the discussion that we can have at the end of my talk in like the QA section, how we address this from the skill set perspective. The other element that I'm going to throw out there is that to be honest, most of the corporations have been creating these transitional teams from existing teams, carving out budgets. So that's another one that we can discuss, and we can be a little candid about that too. All right, let's go. Yes, I have the legal thing too. Mine is shorter. I don't know if that's good or bad. 1, 2, 3, fine. I'm good. So very simple context and what we're gonna do, and some use cases, just as my colleagues before. So our view of the problem, or where we are going with this. So you see here, this is oil products. We are thinking that for 2030, we're gonna be reducing them to a certain extent. It says 30%. That forecast change every 6 months or something, but let's say that is around that. In terms of gas, that's the big jump, right? That's where we're gonna be moving heavily, as our colleagues here are mentioning for their own companies, and electricity, direct ways of electricity providing to customers. Most of these numbers are heavily France and Europe oriented, but we have efforts overseas also to make this happen. This is the big picture. We have new things like biomass and H2, hydrogen, that wasn't there before, and now we have a more diverse portfolio. The idea is 2050 reach, even with these numbers here, higher and reduce even further that. But just as Elizabeth mentioned, we had to sustain that with the old core business, right? So it's all depends on how we balance the game. So this is the big picture. What does this means for us? I think I'm gonna put the mask, killing me. So basically, the corporation realized that this requires a huge effort, and not only in terms of a strategy, but how the strategy is implemented. And that means reorg. Yes, so we reorg like a year ago. A new organization was created, it's called OneTech. What happened here is that OneTech will coalesce all the R&D and technical lines together in one BP ship, basically. And there we're gonna have all the R&D for different branches in one place, collaborating and exchanging knowledge and helping the rest of the branches. But in terms of the energy transition, right? So there are some new elements here. For instance, in the traditional R&D structure, we will have the core geophysics, geology, reservoir engineering, and that was about it. And then a bunch of like a motley crew team of applied math and computer scientists. Now in the transitional world, we have huge teams that are dedicated to these new topics. So that's what I was talking about, budgeting and carving out things. Well, this is where it comes into be, right? In particular, we have offshore wind projects. So we have teams working on simulation, and therefore we have the HPC angle coming in. And because these days we use a lot of ML-based proxy approaches to solve that, we have the ML combined into it. E-fuels were really not there before. This is new for us. And I'm actually working on some of these projects, and we use HPC. You can imagine it's for molecular design kind of situation, so DFTs and so on. And also using ML for some of the predictions of molecules and so on. So again, we have the new element there. Chemical and engineering process is also been, it used to be very lab-oriented, but we are trying to sell more and more numerical-based solutions to them. Automate, speed up processes, improve catalysts, and so on based on ML. So we have, again, ML angle and then HPC in it. And then we have more like everybody is doing these days, and it makes sense, which is CCUS, CCCS kind of problem. So then we have basically a reservoir on asteroids, complex physics. That's HPC in nature, CFD-oriented kind of situation, and ML combined to it to either speed it up or complement. So then that's how different part of this organization fell into the categories that are related to this transition and the HPC. That's the match, basically, that I would like to point out. So in terms of some real use case or field cases, we have Northern Lights, which is a partnership with Equinor and Shell. So this is CCUS. And for that one, we have reservoir, we have ML, and we have seismic. So basically all the traditionals plus ML working on it. For instance, for the reservoir side, we are using USX, which is multi-physics reservoir application solver that we develop in cooperation with Stanford and Lawrence Livermore. And actually that's quite interesting because USX is now part of the ECP project. It's part of the Exascale benchmark suite because the cases we're going to solve are really, really demanding in terms of computing. So that's about that one. Aramis is another CCUS case where this is just off of, I don't remember what is that one. Let me see. Okay, off of Netherlands. And I believe this is also in collaboration with Shell. I have not worked yet in this project, but I do too. And summer, I will be doing some inversion, ML inversion for this case. So we will have traditional reservoir and ML stuff and the seismic coming into play. Then we have other case, like this one is offshore Scotland. That's a very interesting one because of the geology that we're going to solve there. Quite complex. It's small, but it's quite challenging. And others, like the one that Detlef just mentioned, you know, carbon sinks. So we're going to plant a lot of trees in particular areas and make money of that. Not sure how yet, but okay, that's another discussion that we can have, right? Then completely different angle, what we do about batteries. So 5 years ago, more or less, Total bought Saft, which is a company that specializes on battery research and production. They're mostly niche, so most of the people don't know about Saft, but they are mostly used on embedded systems like satellites. They're very strong in aerospace, actually. Military and other kind of situations where battery is embedded, and now the ambition from Total is to take this and make it like a massive retail kind of company. So we work with them in terms of expanding their scope, and this one, what they do and what we're working with them, it has basically all the classical elements of HPC like CFD, or flow simulation on the batteries, the chemical, computational chemistry part, ML, and so on. So I'm working on one of these projects too, so I know this is quite challenging and interesting and important to improve the yield of these batteries, life expectancy, and capabilities. Microgrids, this is one related to just the previous one. So we have scenarios like this, where we have a grid, with or without connection, I mean a microgrid with or without connection to the grid, and we're trying to come up with techniques to improve the stability and reliability of this microgrid, because sometimes these communities or facilities are really off the grid and it completely depends on the generated energy, either by gensets like diesel-based or PVs or wind or geothermal, you name it. So in our case, from R&D perspective, we create something called PingGrid. Paper is there, and it's basically a simulator that combines these elements and allow very realistic data generation for then using management systems to model what's going to be the behavior of this microgrid. In our case, we add a layer of ML on top of it based on RL and reinforcement learning, and this table shows that the traditional way of doing microgrid is rule-based, PCX kind of approach, and we compare it with the RL base, and you see that for some cases, the RL actually manage the network, the microgrid better. So that's kind of our bit here. Yeah, that's all what I have. Now we go into Q&A panel kind of situation. Elizabeth, Detlef, would you like to sit in the tribunal here? And Weichang? Don't be shy. There's no bad questions or inappropriate ones. I like candid ones, so go straight for the money. Questions? Comments? There's one over there.
Thank you. Appreciate it. Thank you. Catalin Morosiano from Cornelis Networks. I have a question. In general, when we talk about the energy, oil and gas scientists, we talk about reservoir simulation, we talk about renewable energy. We heard today about seismic simulation. I'm wondering, especially in the geostrategical situation where we are today, and I mean in our Europe and the Ukraine situation, are there any plans on developing any technologies on transporting the energy from a point to the other beside the pipelines that we have today?
Let me read again the legal part. No investment based on what we said. Okay, go ahead.
Transporting hydrocarbons has always been core business for all three or four companies that I talked about. So you mean something new, right? Is there something new? In the context of renewable energy, I think we're seeing a trend for much more electrification. If you look at the various scenarios, we want to support a system mostly with renewable energies, plus nuclear these days, right? And let's not forget about this. This has come up not just in the last week, it has come up before. Nuclear is a high-density energy source like no other, zero carbon. But it produces heat and it produces electricity. Let's look at electricity. The electricity grid needs to be upgraded spectacularly over the next decades if we want to support a system that relies mostly on zero carbon. So that's a huge trend. It's completely inadequate today to support the ambitions of growth. So that the other one would be hydrogen, right? Hydrogen as an energy vector comes with special challenges. Today the world produces about 70 million tons of hydrogen and has been transporting hydrogen safely for decades. This can be scaled up. People are always worried about hydrogen because it's the old story from Germany where the the Hindenburg went up in flames. But you know, the fact is hydrogen is a very safe transport mode for energy. It's not something we need to be afraid of. So hydrogen and electrification, I think those are paradigm changes we will see over the next couple of decades. Because your question was beyond LNG, right? When LNG, did you consider that one? That's the one we are still using a lot. Yeah. I was just curious to see. I one day we're going to do LNG with batteries, just to carry electricity, you know, and chips. Back there? You have questions?
Did you want to wear the mic?
It's 5 more minutes, so we should be okay.
Thank you. Hello, Brandon with Penguin Computing. First question I have is for Mr. Lee. I really like the slide that you had talking about the improvements that you saw with the core samples in improving the time to results. Is that just in compared to traditional methods? Are you seeing results faster when running a ML model versus traditional methods? Are you seeing improved accuracy? Are those models ones that you're continuing to improve and develop? Or what's the real benefit of applying ML models over traditional methods?
Well, thank you for the questions. Actually, we will ask the same question too when we start the project. So the answer is both. One way is there's a huge backlog. I'm not sure about other companies, but as people gets to the habit of collecting core samples over years, at least in our case, there's a huge backlog of those core samples just stored in the warehouse, and ask a geologist to go through them, label them, taking core samples. The traditional workflow, it's like a US H-1B or visa application, it's hugely backlogged. So there's need to be a way to streamline those things. So that's the efficiency boost. The second case is your question about the accuracy. The answer is yes, but it's relative. If you give a core sample to a very experienced geologist, petrophysicist, he can do a pretty decent job, give you probably very high accurate results, especially get down the carbonate, sandstone, other things. But if you would say, could you do the same thing over large volume reliably, that's debatable. So we're trying to answer your question, we're trying to reap the benefits of both. Streamline workflow, especially if you train a network. So we're not actually claiming a single uniform network could do well on all different kind of core samples. So you have to build, this is a little bit technical detail, you have to build slightly different models for different type of rock core samples. But once you finish training, and then you apply them, the testing in inference phase is pretty fast. And that you can integrate with the whole workflow and get the benefit on both sides. Does that answer the question?
It does. Thank you. I really appreciate that. I also had a general question for the panel, maybe actually the other three members. I saw that in pretty much all slides or all presentations, you'd mentioned a growing distribution of the workload and renewables, specifically around wind, and then looking at weather models. Are you seeing that as a growing use case for CFD in your HPC applications? And what does that change in look like for your workloads?
Yeah, I mean, I think that's something we've looked at and we've experimented with a little bit. I think it's a bit early to speak to how far we're going to get in terms of weather modeling. I think if we see it as a differentiator, something that can set us apart in the industry, then we may choose to focus on it and, like I said, choose to become experts and leaders in that area. But it is very experimental right now.
Yes and yes. So with the drive towards renewables, the intermittency problem becomes an obvious problem. And then we need to be able to predict the weather much more locally and on different timescales, hourly, monthly, daily, but also seasonally. If we put a wind farm down, we want to make sure there is wind there in 2050, right? And at least with a good amount of chance. And so weather simulations at all scales of time and space will play, are already playing a big role. And then, yeah, just the example of wind farm CFD is growing in our portfolio. These are serious simulations of the HPC scale. You know, these wind turbines in wind farms interact with each other. You can see it on the simulations, and you would place them differently depending on the results of your simulations. Another CFD application area, I think Mauricio showed it, was chemical engineering. New processes for like waste to fuels, right? You can imagine it's a very difficult problem to solve, and computationally extremely demanding because there's reactions on top of CFD.
Yeah, about the wind, we have a collaboration with the NRL National Lab to simulate this at scale with their capacity. Like Detlef said, we need to know different time scales. That's complicated forecast efficiently connected to those. For instance, I'm working on connecting that kind of forecast with the grid, because some of those communities depends on the grid, and we had to keep stability. So then we, add the batteries to keep it more stable, and it plays a role in larger problems and complex problems. And in terms of production, we are actually working with Google on this. So we have a global wind forecast solution with Google, and that's, I think we're going to publish soon something about it. So yeah, it's really a problem, complex, and it all depends of time scale you want to try to solve it and how reliable is going to be your prediction, right? Which can be critical for, like I said, communities that depends on a local grid, or just from the economic feasibility of designing these wind farms in specific locations. Okay, I think we have time for one more, and that's it. Yeah.
You're going, Franz Steinbacher, AWS. We are here at the universities. I want to ask, all these new technologies, especially in renewables and energy transition, need a lot of research, a lot of ongoing advanced research for which we need talent, preferably HPC plus ML plus domain expertise. How easy or difficult do you find it to attract this talent? Because all industry is seen as sort of bad guys, despite of the investments in energy transition, right? Does this energy transition workload attract more talent compared to finding somebody for reservoir simulation or seismic processing, or are you struggling getting these advanced people?
Yes. We have struggled to find people interested in scientific computing, computational fluid dynamics, geophysics, anybody with digital skills and a domain science set of skills, right? Anybody with digital skills tends to end up in the Googles and Amazons and places like that, right? And well, you asked the question, right? So it's been a real struggle, and so we're trying to develop people internally to transition their skills, from one science to another, or from a science to a computational science, and then also struggling to hire externally as well, graduates and experienced hires. I don't know about your experience.
You don't have an easy time hiring talent either, right? So I think we share the competition here. Naturally, I'm not so sure. Yeah.
Then you find these sort of emotions, right?
So our academic engagements have greatly increased. One way to do it, is work much more closely with the universities. I will teach a class this afternoon here at Rice on data science. So that's one way of doing it. All energy majors struggle with a reputational issue, more or less depending on which part of the globe they operate. In Europe, it's really hard to attract talent because of a reputational issue as oil and gas company. It's not as much of an issue here in the US, and probably even less in the Asia space where we believe all the growth sits. But yes, we share the pain. More academic engagements, more external engagements, bring the people in, show them what we really do, publish much more to be present. I always show our people in Shell, Amazon.com/science. I think that's a good portal, and we don't have it, but we're working on it.
Well, thank you. It's a good question. Just to give you a quick answer, we're still hiring, and we got a lot of applications. And for those of you who are looking for a job, feel free to reach out to us. Actually, it's funny that I had two graduate interns last year. They both got offer from Facebook. So they're probably, but I think we also got someone from AWS too. So it's a mutually flowing. And I think I agree with my co-speaker's suggestion. I think I can give you one interesting anecdote. Around 2017, my background is actually electrical engineering and computer science. I've known nothing about our industry by 2008. But I went to Berkeley, talked with the group that developed Cafe for the deep learning stack model. And the professor we had a good discussion. In the end, at lunch, and I asked him, I said, you have a lot of good students. Would they be interested in spending summer with us? And he just burst into laugh. He said, why? My students are booked. Why he had to work for? But I think things are changing as we start explaining to people. There are interesting technical questions. There's a lot of fundamental connections between those technical challenges versus what I call the canonical machine learning applications. There's a lot of relationship between medical imaging, machine learning, versus seismic imaging. There's example I showed, rock sample thin section classification versus tissue pathological diagnosis. So I think, also we're kind of people from energy industry, but for DOE, there's also a lot of interesting machine learning HPC. It's not exactly the initial batch of machine learning application to start with, as we all know. So I think it's going to be commonly more acceptable. People move around, and I think it will be better.
Well, and with that, I would like to thank you for coming, and this is the wrap up for this session. Thank you very much.